I have in front of me Quartus because I'd like to show you today the architecture of a simple FPGA. So to do that, we're going to actually create a simple Verilog program. We're going to compile it and we're going to have a look at how it's implemented on the FPGA. I've named it Exam Arch, short for Examine the Architecture. Click the Next button. Empty files. No add files, we'll write our own. Now here, the Cyclone 5 is quite a complicated FPGA. You can follow the same steps that I did and choose the Cyclone 5 and you'll see a much more complicated, the architecture itself isn't that much more complicated, but the insides of an individual logic element is. Also, as there are very many more logic array blocks, you'll find that when you go to view things, you sometimes just get overwhelmed with the large numbers of logic array blocks you have. So we're instead going to choose this Max2. Now technically some might say the Max2 is not an FPGA, it's a complex programmable logic device, but the architecture is essentially the same. The main difference is that an FPGA, it loses its configuration whenever you switch the power off, whereas and so on the DE1 SoC board that we're using, when you power up that board, if you want it to remember the old code, you actually have to configure some external hardware that's also on the board to reprogram, to reconfigure that FPGA each time you switch the board on. A complex programmable logic device is able to remember its configuration, so you don't need to program it. So these guys are great if you're building a simple circuit, you need a few logic gates, then an FPGA would be overkill because you then have to include additional chips there to configure it at startup time. It's better to use one of these guys here. So select the Max2, I want to specify a specific device and I want the simplest one possible. This one's only got 240 logic elements, so when we come to view its insides, we won't be overwhelmed. The settings here don't really matter. I have changed it to Model Sim Altera Verilog just because we use that in other parts of the course, and then we're ready to finish. We will notice when it comes up that our device is selected here on the right hand side. It's a Max2, not a Cyclone 5 for the board, and Exam Arch is the top level module. Create a new Verilog file, module, and I need to match the top level name, Exam Arch. I'm going to have 4 inputs and 1 output. That's more than enough for what we're doing. And I want it to use 3 distinct logic gates. Now if I do this the normal way, Quartus is going to optimize it and these logic gates are going to disappear. These 3 separate logic gates I'm about to write will be combined into a single lookup table due to the optimizations. So to keep the logic gates, what you put in is a special comment, synthesis keep. And so although this looks like a normal comment, the Quartus compiler scans the comments, and if it sees a comment starting with synthesis followed by a word it understands, it actually does something. It actually says, oh, this is a compiler directive, I have to keep that logic gate there. I'm going to do the same, so y is equal to c exclusive or d, and I need this to be kept as a specific gate, so this tells Quartus not to optimize it away, and assign the output to be x or y. End module. So if you do this and you leave off these synthesis keep attributes, like I almost did here, then you'll find that you only get a single lookup table being used for your design. Here I'm going to get 3 different lookup tables, one for the AND, one for the OR, and one for the exclusive OR. Okay, so let's compile this. Say we want to save it, accept the default name, make sure it's in our current project, save it, and then we wait, and we wait, and we wait a bit more, but at least it's not the Cyclone 5, so that this will finish before dinner time. And here we go, it's almost done. And the first thing we're going to do once it's done is go up to Tools, Netlist Viewers, and look at the RTL viewer. This allows us to check that our Verilog code that we entered describes the circuit that we wanted. And we see here that indeed it does. I've got my 4 inputs, A and B get ANDed, C and D get exclusive ORed, and then their output goes through an OR gate to get E. I've got these 2 buffers in here called X and Y. That's due to the keep statement. Remember, if we look at our code, we've asked it to keep this logic gate, etc. Well, specifically, it's keeping the junctions. It's making sure that I will always have an X somewhere and a Y somewhere. And so that's exactly what we see in, where is it? That's exactly what we see here. X and Y have not been optimized away. Quartus could have combined these 3 logic gates into a single lookup table if it wanted, because lookup tables normally have at least 4 inputs. So this could have been done with a single lookup table, but the keep statement here makes sure that I have 3 lookup tables, one for this, one for this, one for this. To confirm that, we next go to Tools, Netlist Viewer, and we can look at the technology map viewer. The post mapping one is fine. We'll look at the difference a bit later between the post mapping and the other one. So this shows us that how Quartus is going to implement the design on this particular FPGA, or complex programmable logic device if you want to be pedantic. And we have 3 lookup tables. So A and B go into this lookup table, and the output goes into this lookup table. Same for down here, and same for over here. For some reason, it's going to use, so these lookup tables we'll learn have got 4 inputs, A, B, C, and D. For some reason, it's decided to use the A and B inputs for this lookup table, and it's decided to use the C and D inputs for this one. This is just a coincidence and has nothing to do with me calling them A, B, C, and D. And then the outputs here also go into A and B over here. We can actually see this on the particular FPGA, and there are several ways of doing it. Firstly, if I want to know where this particular guy is, I can right click, go down to locate node, and I can do locate in chip planner, and it will show me exactly where this particular lookup gate is located. Another way I can see what's going on is by going to Tools and selecting chip planner here. We ignore the request to pay lots of money and click OK. And here is our FPGA. I can zoom in a bit if I'm sufficiently clever. And what do we have here? So around the outside here, we have got our input-output buffers, input-output logic. And we see that we are using 1, 2, 3 different input-output blocks. And inside each one, we can actually see that we're using this pin, and this says it's node C. So our input C is actually going to be connected to the pin that comes into here. Over here, I have got my B is going into this particular pin and into the circuitry associated with that, which we'll see presently. This one here is E, that's the output. And over here, I have got my D. Now this software is not perfect. I was wondering where my A is, and it's actually up here, node A. It just forgot to color it for me up here. Never mind. If you're having trouble seeing things, we can come over here and turn off unused resources. And so this makes it clearer. Now we can see we've got our input A, our input C, our input B, our output E, and our input D. Here are our three logic gates. So I've got a logic gate here, a logic gate here, and a logic gate here, which corresponds to my circuit, right? 4 inputs, 3 logic gates, 1 output. If I turn the unused resources back on for a moment, then we have around the outside our input-output blocks, and inside in blue, these are our logic array blocks. So I like to think of them as apartment buildings. We have 10 tenants to each apartment building. Belonging to the same apartment building means that you share the same plumbing, you share the same electricity, the water pipes, etc. And information can be transferred quickly between these tenants because they all live in the same set of apartments. And then you've got your neighbours, and down the road some more people, and around the corner some more people. So here are all our logic gates. They are inside logic elements, which are these individual white things, and these are inside logic array blocks. So we have a nice array to work with here. And we need to be able to wire up. We need to be able to send an input into our logic gate, send the output into another logic gate, and send the output of that to the output pin down here. So how's this wiring done? Well, first let's have a look at the actual wiring. So with my selection tool selected, I'm going to select everything like that. And then over here, I can have it show me the fan out and have it show me the fan in. And if we have good eyesight, in fact, I'm going to try to zoom in a bit for you here. If you have good eyesight, then what we see here is that input A goes to this logic gate here. Input B goes to this same logic gate, which is what we expect. And then its output is going to go to this logic gate here. And similarly, this input here is going to this logic gate. One of these inputs, if I can get it highlighted, sorry, it's this one. This input here is also going to here. So C and D come in here, and then the output here also goes to this guy over here. And then its output goes down, bang, to this output pin here. So we see how we've wired up from the input through our logic gates to the output. Now this is just a graphical representation here. How does the actual wiring work? Well, if we come along here and we can look at the routing details. Now it's still not shown here because I'm not zoomed in enough, but I'll turn it on anyway for next time. And I can look at the global one here. And as soon as I add the global one, you notice how we've got these highways. These guys contain wires that we can use for routing. So if we have to get a signal from here, this signal is basically going to travel up to the highway, along the highway, down into the apartment block, and then gets into my doohickey here. If I were to zoom in some more, maybe we can actually see that. So now I've zoomed in, I can see some more of the wiring. It's not exactly the wiring, it's the schematic wiring, but the principle's correct. So from my input coming in here, input C, it makes its way up to this superhighway. The information zooms along this superhighway here, and then it comes down this superhighway into here and somehow into this guy here. There will be a PDF document that explains the architecture of this MAX2 device if you want even more information. But the basic principle is that we've got these highways, we've got these local roads. At every junction there's a switch. FETs are just electronic switches, so what happens when you configure the FPGA is that you store into memory what each switch should be. Should it be open or closed? And the memory just gets sent out to each of the FETs to actually do the opening or closing, to work out whether there is a connection between intersecting wires or not. I just changed the zoom and switched off unused resources so I can see it a bit better. So we see how the input here somehow makes its way up to this highway. It then zooms across and it's somehow connected into these guys in here through the wiring. So it's not shown exactly, but it does give a good illustration of what's going on, how the connections are made. Let's now have a look at an actual logic element. So let's have a look at this logic gate. All I need to do is hold my mouse over it and double click, and here we see exactly what's inside that logic element. Now if you do this with a Cyclone 5, you'll get a much more complicated diagram coming up here, but importantly the main principles are always the same. And the main principle is simply that we have here in blue a lookup table, and we have over here a flip-flop. And every logic element on any FPGA is going to contain a lookup table and a flip-flop. Those are the core ingredients. The other circuitry has got to do with different FPGA manufacturers wanting to try to make their chips faster than their competitors. The Altera chips are set up to be able to do fast addition. If you want to add two binary numbers together that have got 8 bits or 16 bits or whatever, then you need to use a lot of logic elements, and they provide additional interconnects and additional logic so that within one apartment block, within a logic array block, you can connect these logic elements together so they become high-speed adders. So they can add faster than if they didn't have this additional circuitry here. We don't need to worry about that. We just need to understand that inside FPGAs, you've got your logic elements, and each logic element contains a lookup table and a flip-flop. And remember, all digital logic is made using either lookup tables or flip-flops. In this particular case here, we see how it's configured, this logic element. Each logic element is highly configurable. These are FPGAs because you configure them. And in particular, we can choose for each logic element whether we're going to use the lookup table, or whether we're going to use the flip-flop, or even whether we're going to use both together. So the blue lines show what it's chosen to configure this particular logic element to be. If we look over here at the property name, then we see that the full name is the module name, exam arch, and Y, pin Y. So this output here is going to be my Y. The location string tells us which logic array block it is. So we're 4 across and 2 down, and N2, that means it's the second tenant, it's the second logic element in the logic array block. The sum LUT mask. LUT is lookup table, and this mask tells us what truth table this lookup table is going to implement. Now, if you can convert this to binary very quickly in your head, and then think of the full truth table, you can actually work out what it's implementing, but it's easy to look down here to see the mathematical equation for it. Now, don't ask me why they don't have an or sign here, they have a dollar sign instead, but the principle is this tells us that the output of the LUT is going to be the input B ORed with the input D. And you can also deduce that from how it's configured. This is the number that's actually written into this logic element's lookup table to make it do its job. Data B over here, if we have a look down here, we see that data B is our input C. So input C comes in here. This guy, it's the input D that's coming into here, and so it gets, presumably that's an ORed, it gets ORed together, and the output goes out to combinational out. If we scroll down here, so we see that all these things here, so carry in and all these things needed for doing fast addition or for using the flip-flop, they're all disconnected because we're not using those we're not using the rest of this circuitry up here. So it's highly configurable, and each logic element just gets configured to do the task it needs to do. In our case, we have a very simple task, just configure the lookup table to do its job, and then we use inputs B and a D here to go through here, bang. Having looked at logic elements, and they're all the same, all that determines how the FPGA works is the wiring between the logic elements and how each logic element is configured. So having looked at one logic element, we've seen them all. We can now look at the inputs and the outputs. So double click on this input here, and we've got this diagram here. This funny node here is the physical FPGA pin. The part on the left is used if it's an output pin, and the part on the right is used if it's an input pin. Now this diagram doesn't show the additional processing. To see the additional processing, then you can have a look at the Max2 user manual where it describes the architecture. That document is in the lecture notes included as a PDF. We have a look up here, the full node name. We see that it's pin B here. The location string is the exact pin number this guy is. It's being configured not as an output but as an input. So the signal comes in the pin, then through this time delay we'll talk about in a second, and then to the FPGA board itself, where it disappears when I move my mouse, where we see that the signal name is capital B in our Verilog code. It's not using a weak pull-up, we don't need a slow slew rate, etc. These things, if you want to understand them, you look at the user manual for the Max2 complex programmable logic device. The input-output standard says that it's 3.3 volts. So the circuitry, it comes in the pin, then it goes through an appropriate buffer to convert it from the 3.3 volts that it's configured for to whatever the internal voltage is for this particular FPGA. For the Cyclone 5, I believe it's 1.1 volts internally. This delay here, we can turn it on and off via here. You can right click on it, turn it on or off. Until we learn about timing later in this course, it's hard to explain the purpose for this delay here. The guide does say it's to ensure zero hold time, and once we learn about how flip-flops work, etc., that will make more sense. Returning to our diagram, that was an input. This particular one is an output, and we see that because it's an output, we're now not using the part on the right, we're using the part on the left. So remember, these guys are highly configurable. Each pin can be either an input or an output. That's part of the configuration. So now this pin's being used in input mode, and we see that it's being used as output, and we see that the signal coming, that's going to be sent out the board. If we have a look here, it's named capital E in our Verilog code. It goes through a nice buffer and out through the pin there. We can read off the same information down here. Pin E is what's going to be sent to the pin. Up over here, we see that the input-output mode is indeed in output mode.